As the next subject in lecture number 7, we're going to talk about relative motion. Actually, we have talked about relative motion in kinematics section of this course about particles. However, we're going to relate the Newton's formula here for the relative motion. Now, the relative motion we're going to be talking about is for an observation frame, again, that is observing the same particle's motion, but this observation frame is in motion. The type of motion it does is translational motion. There's no rotation of the observation frame. And in the figure on the left, the frame with an origin at B is the observation frame that is moving or translating, better to say. And there's the inertial frame with the origin O, and this particle's motion is also observed from this point O. The vector associated with the observation from the inertial frame is named as r with a subscript of a, and the observation done from the translating frame is named as r a with respect to b. Just take off my pencil tool. Okay, so this is our vector defining the observation that is done from the frame that is translating. This is the frame with the origin at B. And we're going to name this vector from B to A as R relative. Now, in the kinematics section, we have already discussed about this equation. RA is equal to RB plus RA with respect to B. Now we term it as R relative. And then in the kinematics section, again, you will remember that we took the derivatives of this equation with respect to time. One time we get the velocity equality, the second time we get the acceleration equality. So if we do the second derivation with respect to time, we get an acceleration of A, this is our particle, acceleration of A is equal to acceleration of B, which is the translating frame, plus the acceleration measured from the translating frame with an origin at B, which is going to be A relative. So with respect to these derivations, we get this equation. We already derived this equation in the previous lectures. Now this acceleration of A with respect to B is V dot relative or R relative double dot. And then actually these are vectors, and then you can use any coordinate frame to do your resolution. You can use a rectangular coordinate frame. You can use a polar coordinate frame if you are working in plane. If you're not working in a plane, if you're in a three-dimensional environment, the problem happens in a three-dimensional environment, then you might as well use spherical coordinates, cylindrical coordinates to resolve these vectors. Anyways, that's not the point. We already discussed about these in our kinematics section. The point here is that we can actually adapt the Newton's equation F equals ma to our relative motion concept, because the acceleration in Newton's equation, this acceleration of A, is an absolute acceleration always. This is an absolute acceleration vector. Now, we already defined this absolute acceleration of A, measured with respect to an inertial frame, to be the acceleration of an observation frame that is in motion, the acceleration of B, that is, and then the acceleration measured from this observation frame, this is the A relative. So we can substitute that information now in the Newton's equation. And as a result of that, we will have a two-vector information inside parentheses, addition of these two vectors. And again, you can use any frame, any type of coordinate system to resolve these vectors. Now, based on this information, let's see what kind of derivations that we can do. And these derivations are based on the investigations of D'Alembert. The first investigation that we're going to do is taking a look at this formula and then sketching this formula on for a particle like that, and I'm using the inertial frame coordinates x and y, and there's our particle. If there's this resultant force acting on the particle denoted with the red arrow here, then the acceleration of the particle should be in the same direction, and then these are going to be related to each other by this mass. Okay, so this is pretty simple. But then if we attach a coordinate frame to this particle, which is shown here with the small caps x and y, and this coordinate frame is moving with the particle, then with respect to this coordinate frame, the particle is in a static condition, which means it doesn't move, as observed by the coordinate frame that is attached to the particle, because it's moving with the particle, and that makes sense. In that case, if this is a static condition and a resultant force is applied to this mass, then there should be an equal amount of force in the opposite direction for this particle, so that it's going to be in a static condition with respect to its own frame. So with respect to its own frame, we can say that it has a force that is equal to mass times the acceleration, the actual acceleration of the particle in the opposite direction. So as investigated in its own frame, then there will be a force equilibrium, no motion of the particle in its own frame, and its own frame, it's going to experience this amount of acceleration, which is in the opposite direction, this amount of force which is in the opposite direction of the acceleration actually, and this is called the D'Alembert forces. Well, we kind of feel this in our daily lives. How do we feel that? For example, you're riding in your car and then you're going to take a turn, right? You're taking this turn with your car, and as you're taking this turn, actually, if you're moving in a constant speed, even if you're moving in a constant speed, there is the acceleration of the car towards the center of the circle. Okay? However, how you feel inside the car while you're handling the wheel of the car, steering wheel of the car, what you feel is actually a force that is trying to push you out of this curved path, and this is actually equal to negative m times a, and this a is the normal component of the acceleration, by the way, and this is what you feel in your own frame, because you're making this feeling in your own frame. This is similar to also an example that we did earlier. If you remember, there was this curved path and we had this block, and this block was on top of the curve, and we were trying to calculate the normal force, right? So there's this normal force applied by the curve to the block. There is the gravitational force due to the mass of this block, mg. And then we said that there is also the acceleration of the block, because it's moving to the right on this curve and it's taken a curve. So with respect to the radius of curvature, it's going to have an acceleration towards the center of the curve. And then the type of equation we wrote was based on this information as n, if we say that's the positive direction, minus mg, that is equal to in the negative direction, we have this minus m times an. Okay, that's what we wrote actually before. Now, based on this information, by taking this acceleration component in its own frame as a force, now we can do a static equilibrium. We can just work out the forces and say that if there is an acceleration towards the center of the curve, then the D'Alembert force associated with this acceleration is in the upward direction, and the amount of this force is m times an. But then this time it's in the vertical direction, vertically upward direction. So if we write out the static force equilibrium, summation of forces, then we're going to write n plus this time m times an, this is our D'Alembert force, minus mg, because of its direction is downward direction. We accepted the vertical upward as positive, and since this is static equilibrium, the summation of all forces should be equal to 0. And if you take a look at these two equations, they're actually exactly the same of each other. But in one case, we make use of the D'Alembert forces and investigate the system as a static case. In the other one, we make use of the free body diagram of the block and use the Newton's equation.